All right, let's just jump right in. If you've ever written even a single line of code, or heck, even just used an app that decided to crash on you, well, you've already met a software bug. So today, we're going to pull back the curtain on debugging. It's this super essential and honestly sometimes thrilling skill of solving these little digital mysteries.
This is a moment every single developer knows all too well. It's that sinking feeling, right? Your creation, something that should work perfectly, just goes completely haywire. And that, right there, that's our crime scene. Something went wrong, and now it's our job to figure out what, why, and how to fix it.
So, to solve this mystery, we first have to identify the culprit, right? So in our first section, let's ask, what exactly is a bug?
At its core, a bug is really just any unexpected behavior. It could be something super small, like a button showing the wrong color, or it could be absolutely catastrophic, like a security flaw that leaks private data for millions of users. So the scale can be wildly different, but the root problem? It's always the same. The code just isn't doing what it's supposed to do.
And you might be surprised where the term actually comes from. I mean, it's not just a metaphor. Way back in 1947, the computer pioneer Grace Hopper and her team found an actual moth, like a real insect, stuck in a relay of the Harvard Mark II computer, and it was causing it to fail. They literally taped the bug into their logbook and debugged the machine, and, well, the name just stuck.
Okay, so if we have bugs, we obviously need a way to catch them. And that brings us to the main event, this art of detective work that we call debugging.
So what is debugging? It's really just the systematic process of hunting down these bugs and, neutralizing them. This isn't about randomly changing code and just hoping for the best. No, it's a disciplined investigation into the logic of a program.
And this highlights that every single debugging session has three really clear goals. First, you've got to isolate what went wrong. That's the symptom. Then you dig deeper to understand why it happened. That's the root cause. And finally, you put in a solution that actually fixes the problem, hopefully without creating a bunch of new ones.
Right. Every detective needs a toolkit. And coders have a pretty powerful set of tools and techniques they can use for gathering clues and cracking the case.
Let's walk through some of the essentials. First up, you have print debugging. This is the classic method, right? You just sprinkle commands through your code to see what's happening on the inside. It's fast, it's simple, it's kind of like leaving notes for yourself. But then you have modern debugging tools, which are way more powerful. They let you pause the program entirely, like you're freezing time, to inspect every single detail, line by line. Now, your most direct clue is often an error message. This can pinpoint exactly where the system broke down. And finally, there's automated testing. Think of this like a preventative security system, running a whole battery of checks to catch common bugs before they ever get to a user.
And then there's my personal favorite, rubber duck debugging. I know, it sounds silly, but trust me, it is incredibly effective. The idea is you force yourself to explain your code step by step to some inanimate object, like, you guessed it, a rubber duck. And so often, just verbalizing the problem out loud makes you see the logical flaw all on your own. It's like you become your own detective's assistant.
Okay, theory is great and all, but let's see this detective work in action. We'll use a simple, super common case that trips up coders all the time. So, the investigation begins with our very first clue, an error message, index out of range. You see, this message is like a witness pointing to a specific location. It tells us we tried to access something in a list that just doesn't exist. So we know exactly where to start looking.
And here we can see the crime and the solution, side by side. On the left, we've got a list with 3 items. Now, in most programming languages, lists start counting from 0. So the valid positions are 0, 1, and 2. The buggy code asks for position 3, which doesn't exist. And boom, the program crashes. The fix, on the right, is super simple. We just ask for position 2, which correctly gives us the last item, the number 3. And case closed.
So we've solved our little mystery, but why is this detective work so important in the grand scheme of things? I mean, why does debugging matter so much?
Well, because without it, the digital world we all rely on would literally fall apart. Good debugging prevents your banking app from crashing when you're trying to make a transfer. It's what ensures a smooth, frustration-free user experience. And critically, it patches security holes that could otherwise be exploited. But also, for the developer themselves, it's the ultimate training ground for logical thinking.
So what this all really means is that debugging is way more than just cleaning up messes. Every single bug you find and fix is like a mini lesson in logic, a deeper insight into how systems really work. It's a skill that sharpens your mind and turns a good coder into a truly great problem solver.
So the next time your app freezes, just remember the detective work that's happening behind the scenes. And hey, if
If you thought that little indexing error was interesting, just wait until you hear about the bugs that cost billions of dollars and sent rockets careening off course. We'll explore those in our next explainer on the most famous bugs that changed technology forever. See you then.